Let's now continue our survey of elementary functions, continuing with the trigonometric functions. These functions arise when we consider right-angled triangles and circles. Let's have a look. If we start with a right-angled triangle, here, where I've chosen the length of the hypotenuse to be 1, then we can think of cosine and sine as defined by this triangle with cosine of x as the length of the horizontal and sine of x as the length of the vertical, where x is this angle in here. So from this, we can see that they must obey the fundamental identity from Pythagoras' theorem, cos squared x plus sine squared x is equal to 1. So this is a starting point for trigonometric functions. What do these functions look like? Well, we can figure this out if we take this point on the unit circle and imagine moving it around the whole circle so that the x increases from 0 to 2 pi. Let's see how that works. So here's an animation where the point on the unit circle increases round anti-clockwise way, which is positive in the mathematical sense, and it increases around the circle from 0 to 2 pi and then repeats itself. This traces out the following two functions. If I consider the vertical line here, going up and down, this traces out the sine function, and if I consider the horizontal direction, this traces out cosine of the function. And we can see the familiar sinusoidal oscillation for both of these graphs. Once we generalize this away from a single circle, we can think of the functions as continuous functions of x for all x in the real line. And so here's a picture of both sine and cosine of x, and they have two ways to distinguish them. The first is that sine x starts at 0, rises up to 1, and then comes back to 0 at x equals pi. Then it goes negative, down to -1, and then back up to 0 at 2 pi. So once we get to 2 pi, it's completed one cycle. Cosine is basically the same function but offset by pi by 2. So it starts at 1, drops down to 0, and then back up to 1 at 2 pi. And if we just remember where these come from the triangle, then sine, being the vertical length here, means that it goes from 0 when x is 0 up to 1 at pi by 2. One thing we should mention at this stage is that we're using radians here, we're not using degrees. In maths we always use radians. So just remember that pi radians is 180 degrees. So pi by 2 corresponds to 90 degrees, which is a right angle, and so on. In fact, when we deal with trigonometric functions generally, there doesn't necessarily need to be an angle involved. So whenever there isn't an angle, it can just be a real number. X is just some real number. Once it's converted to angles, this means it's in radians, not degrees. So I mentioned these functions are kind of the same function, but just shifted by pi by 2. We call this that they're out of phase with each other, and in fact they obey the following identities. Cos x is just sine of pi by 2 minus x. And similarly, sine x is a cosine of pi by 2 minus x. So these functions are out of phase with each other. A further thing that we can notice if we look back at the graph is that sine is what's called an odd function and cosine of x is an even function. This means for cosine, which is an even function, cos of a positive value of x is the same as cos of the negative value of x. And for sine x, sine of a positive value of x is minus sine of the same value of x. So cos is even, which means that cos of minus x is cos of x, and sine is odd. Both functions are periodic, which means if I add on any multiple of 2 pi, then I return the same value of x. So cos of x plus 2n pi, where n is any integer, positive or negative number, then I get cos x, and the same for sine. A further important relationship between the two functions is the addition theorems. So these are if we take two numbers, x and y, add them together and take the cosine or sine, then if I take the cosine of x plus y, I get cos x cos y minus sine x sine y. Similarly, sine of x plus y is sine x cos y plus cos x sine y. All the other trigonometric identities that you know involving sine and cos can be derived from these fundamental identities. There's a whole bunch of other trig functions, but again they're all derived straight from these two. So for example, tan of an angle is sine over cos. Of course, as you know from basic trigonometry from triangles. And then there's auxiliary functions, which are kind of a shorthand really. So these shorthands, sec x, cosec x, and cot x, are just 1 over the functions cos, sine, and tan respectively. We'll use these quite a lot as a useful shorthand for those functions. It's useful to have a quick look at these. Tan in yellow is probably the most important. Let's have a trace from one of minus pi by 2 through to pi by 2. So tan is sine over cos, so whenever cos goes to 0, tan shoots off to plus or minus infinity. That's indicated with these points where the function is not defined, with these dashed lines here. These are known as vertical asymptotes. We'll come back to this later in the course. We also have sec x and cosec x in blue and brown. So sec is 1 over cos, so again has the same vertical asymptotes as tan, and cosec is 1 over sine. It also has vertical asymptotes, but now at 0 and pi and integer multiples of. We now come to the slightly subtle concept of defining inverse trigonometric functions. The tricky thing here is that the functions are not one-to-one. Because they're periodic and they repeat every 2 pi, they do not pass the horizontal line test which we require for an inverse function. So in order to find the inverse trig functions, we need to select just a patch of sine or cos, which is one-to-one, and then define the inverse just over that range. Let's see how this works. Let's start with the inverse sine function. So for the inverse sine function, we're going to define this as sine minus 1 of x, in keeping with the inverse notation, but we're going to also use the notation arc sine to denote this. And for this function, we're going to choose just a patch of sine which is one-to-one, and that is a patch of sine which is defined between minus pi by 2 and plus pi by 2. So in this region, sine looks something like this. And if we invert that by reflecting in the line y equals x, we find a function that looks a bit like this, where inverse sine is defined in the interval minus 1 to plus 1. So given this inverse then, we write, and therefore the inverse sine of sine of x is equal to x, provided x is in the region pi by 2 and minus pi by 2. If x is outside of that region, one needs to add on sensible multiples of pi in order to get the answer that you're after. Similarly, sine, the inverse sine of x is x provided x is in the region minus 1 to 1. So the same goes for cosine. For the inverse cosine function, the region that's selected as 1 to 1 is the part of the real axis from 0 to pi. That then defines an inverse cosine function. For tan, we can find the inverse function of tan if we just consider the part of the real line from minus pi by 2 to plus pi by 2. So let's just go through these quickly. Arc sine, the one we just looked at in blue here, the arc sine function is defined between x equals minus 1 to 1. It's this blue curve here. Arc cos is the part of the cosine function from 0 to pi, reflected in the line y equals x, and results in this function here in brown. And arc tan is the function in yellow here, which tends from minus pi by 2 as x tends to minus infinity, and tends to pi by 2 as x tends to plus infinity. So that's about how the functions look. There's a little bit of trickery in fiddling around with these functions in order to make sense of them. Let's have a quick example of how to simplify one trig function of another's trig's inverse. So let's take as an example, try to simplify the tangent of the inverse secant of x. So let's see how we can go about this. When dealing with inverse functions, let's let y equal the inverse of the secant of x, which means that x is sec y, which is just 1 over cos y. Okay, so that means cos y is 1 over x. Now, if I draw a right angle triangle to go with this picture, this is a really useful trick in order to simplify these sorts of problems. Let's draw a triangle with y is one of the angles, cos y is 1 over x, and if I use my trig rules, I have 1 over x, my triangle, which means that the third side is the square root of x squared minus 1. So I could now read off what sine y is and what tan y is. So in fact, this implies then tan y from this picture is opposite over hypotenuse, which is x squared minus 1, square root of x squared minus 1 over x. And of course, tan of the inverse secant of x is what I'm after. Since y is the inverse secant of x, I now know that tan of sec minus 1 of x is just the square root of x squared minus 1 over x. So it simplifies into an algebraic function, which is probably quite surprising. And you can play the same trick with any trig function of any inverse trig function and any inverse trig function of a trig function.